Chapter 16, and this is thermodynamics. So last time we got into a little bit of it after the quiz. So remember that thermodynamics, a lot of what we will deal with is, again, the idea of whether or not a lot of times the reaction is spontaneous. And as we talked about last time, the idea of spontaneity in this sort of application, again, really has nothing to do with how fast or slow reaction will take place. It just really sort of answers that question of, will the reaction actually take place under those particular conditions? Again, you could have a spontaneous reaction that takes place very fast. You could also have a spontaneous reaction that takes place very, very slow. So again, what we're talking about here again is that whether or not the reaction will actually take place. As we talked about, kinetics, like we did earlier on in the semester, really deals with maybe how fast or slow the reaction is proceeding, but thermodynamics here deals with that other aspect of it. A couple of important thermodynamic values that we talked about and that you've talked about in previous classes as well, again, is our delta H and our delta S. Once again, our delta H is our enthalpy, which is sort of the heat of the reaction. And again, as we've talked about a number of times up to this point here, obviously we have that negative value for delta H. We are dealing with our exothermic process. If our delta H is positive, it is endothermic. Delta S, on the other hand, is the entropy. And it really does sort of measure the, however you want to look at, but we'll talk about disorder that's happening. And when we have sort of the change in entropy, if the amount of disorder is increasing, it actually becomes more positive. So if the amount of disorder increases, the delta S here will result in a positive number. If the amount of disorder decreases, which on the other token of that would be there's more order happening, the delta S value will be a negative value. We also talked about, also important a little bit later on in this chapter as well, again, the units there, these guys are typically joules for delta S and kilojoules, again, typically the units there for delta H. Remember, the other thing when we talk about a reaction sort of being spontaneous is the idea of delta H and exothermic sort of processes. As we saw, I think a list last time, there's a list of some reactions that were exothermic. There's a list of some reactions that were endothermic, and, they were all spontaneous reactions. So as I mentioned, exothermic sort of reactions can sort of favor a spontaneous reaction, but it doesn't necessarily guarantee that the reaction will always be spontaneous. And on the other token, obviously having an endothermic process doesn't necessarily mean that it will not be spontaneous either. So we do look at sort of entropy here to help us decide that. At the very end, I think we finished up with the idea of entropy, like enthalpy, they are state functions, right? And state functions basically mean that really the only two important aspects of the process is basically where you start and where you end, basically. Kind of your final and your initial sort of states are really the two really important parts of it. And that's why when we calculate, for example, something like delta H, we take the delta H of the products minus the delta H of the reactants. And same thing with delta S, as we saw, we could also calculate the delta S for a reaction by going to a table and taking the delta S of the products minus the delta S of the reactants. And that, once again, is because when we look at a chemical reaction, we have reactants that go to products, and obviously our products are really our final state, right? And our reactants are our initial state. So again, when we kind of do products minus reactants, that's essentially what we're doing when we sort of take calculate something like delta H or delta S. Any questions on any of that stuff? I think we covered last time there. Okay. So the first law of thermodynamics states that energy can be converted from one form to the next, but it cannot be created or destroyed. That again is all that enthalpy stuff that you talked about in the previous class, as the conservation of energy. The second law of thermodynamics is what we're going to focus on here today, and that is the entropy of the universe increases in a spontaneous process and remains unchanged in an equilibrium process. So when we use something like entropy to help us determine whether or not a reaction is spontaneous or not, we typically need to calculate a certain thing, and that is actually what is known as the delta S of the universe. So to figure out whether or not a reaction is spontaneous, you do need to calculate the delta S of the universe, which is basically made up of the delta S of the system plus the delta S of the surroundings. That is basically everything, the system and the surroundings. The system in a lot of cases is also the reaction. So sometimes it's referred to as the reaction because that is usually what you're interested in, right? Whatever's going on in your beaker or your test tube. And then obviously everything outside of that would be your surroundings. So if you calculate the delta S of the universe by figuring out the delta S of the system plus the surroundings, and you do get a positive value, then the reaction would be spontaneous. So if you get a delta S of the universe where it is positive, it will mean that that reaction is a spontaneous process. And if it is a reaction, what that will essentially mean is we would expect the reaction to proceed from reactants to products, basically. That's basically how it's written, is what we would expect to happen. If you calculate the delta S of the universe and actually equals 0, that means you're at an equilibrium process. So there's kind of no net change in the disorder, right? So when you reach equilibrium, things are going back and forth at the same rate, which means you can't get any craziness happening on one side or the other because everything's sort of locked into place, right? So when you're out of equilibrium, things are moving to reach the equilibrium, for example. So that's where you could have obviously a little unbalance in terms of the order or disorder. But when things sort of reach equilibrium, everything kind of stays the same. Not that you have the same amount of everything on both sides, but everything is pretty much locked into place where they're at. So if you do calculate the delta S of the universe and it is obviously a negative value, it would mean that this process is a non-spontaneous process, which means under normal conditions, you would not expect a reaction to proceed from reactants to products, basically, is what that basically means. Any questions on that there? We're going to talk here in a second on how to calculate each of those, both the delta S of the system and the delta S of the surroundings, which is a little bit different calculation depending on sort of which one you are calculating. So let's start with actually how to calculate the delta S of the system. Again, also the reaction. For the most part, if you're pretty much just given a reaction or an equation, you're going to go to a table and you're going to calculate the delta S from the table values. So you'll go to the delta S table and you'll find all those values. Remember, I think what we talked about at the very end last time was it's a little bit different than, say, a delta H table. Besides the units, you will also find values for things that you typically find no values for or 0 values for delta H's. So again, things like H2N2, things in their uncombined natural state, you will actually have values for, unlike what you will see in delta H tables where they will be 0 for those guys. In addition, delta S values are typically all positive values. So that's also a little bit different. And lastly, as we talked about as well, you want to always make sure that you find things in their correct state when you go to those tables, that you just don't sort of pick the first one, which might be the incorrect state. So basically, we want to calculate the delta S of the reaction, which is basically the same thing as the system, by taking all the delta S's of our products minus all the delta S's of our reactants. Again, really our final state minus our initial state. Just like what you do with delta H, if you do have a coefficient, you need to multiply the coefficient by the value you find in the table. And again, add them all together. So let's take a look at this. Here are some of the values that you can find from the table, except I'm missing one. Might be a good one to know. Do you have it on yours? I feel like you have it on your notes. What is the CO2? Thank you. 213 even or 213.6. Thank you. All right, now I have everything you have. There you go. All right, so why don't you take a moment here, calculate the delta S of this reaction. And again, obviously, these would be values you would find in a table, like in the back of your book or something like that. So once again, obviously, if they were not provided for you, you'd go find these guys in a table. We're just going to, again, take all of our products minus our reactants. So the delta S here of our reaction, which is our system, would be our product. So there's 2 times the value for CO2, which was 213.6. We're then going to subtract all of our reactants, which would be 2 times the value of CO, 197.9. We're then going to add our other reactant in there, which was O2, and there's only one of them, so that's 205. Big bracket over that. All right, so if we do all that good stuff there, 2 times 213.6 minus 2 times 197.9 plus a 205. Looks like we end up with a minus 173.6 joules here. First off, any question on the calculation there? So the key here is you got to make sure, again, you take those coefficients and you multiply them through. Now, does this tell us if this reaction is spontaneous or non-spontaneous? The answer is no, because this is just the delta S of the system. It tells us, is the order increasing or decreasing in this case? So what's happening here with the amount of disorder? Are we increasing the disorder or decreasing the disorder based on the value? We are decreasing the amount of disorder because it's a negative value, which means the amount of order is increasing, right? So that's what it tells us. And one nice thing about sort of doing these calculations is you can make a prediction from just looking at the equation. So if we just look at the equation, for example, here on the left-hand side, how many gas molecules do we have? We have 3 gas molecules. And on the right-hand side, we have 2 gas molecules. So we're going from a situation where 3 things are flying around to only 2 things flying around. So we're going for a lot more disorder to more order, which we could predict that our delta S value for this reaction should end up as a negative number, which it did. So again, that's the way you can kind of check yourself by looking at that. So whenever you kind of look at a reaction and you sort of end up with kind of more gas molecules than you started with, that would increase the amount of disorder, right? More things flying around and more energy. Or if you do, like in this particular case here, end up with actually less gas molecules than you started with, then that's going to create a lot more order, a lot less disorder, and you should expect it to be a negative number. Any questions on that there? Which is essentially, I think, what this just said there. So once again, obviously, if you have no change in the number of gas molecules, then it will be a relatively small number, and it may be positive or negative depending on which way it moves. But definitely when you have sort of a difference in the number of gas molecules, you definitely can make a pretty good prediction. Not necessarily obviously on the number, but whether it should be a positive number or a negative number, which can be helpful sometimes in case you mess up the math. So for example, if we just look at this equation here on the bottom, we can make a prediction that the delta S should be positive or negative. Yeah, so once again here, it actually should end up being 1 gas molecule. That is a solid. And that is 2 gas molecules, which means we're actually increasing the amount of disorder. It actually should be a positive number here. That's a solid, yeah? Is that a solid? Maybe it's not a typo and I just can't read here. That's probably the case. That is a solid. Look at that. Let me just redo. We'll cut that out of the video. It'll be all right on the replay. It'll be okay. A little creative editing. All right. So once again, I think you were right originally. That is one gas molecule, and that is obviously no gas molecules. I guess that's what the big S means, right? All right. So obviously we are going from gas molecule flying around to no gas molecules flying around. So that creates a lot more order. So the delta S here should be negative. Good. All right. Because I can retype it as a gas and redo it one more time, and then you can have any version of the video you like on that one. All right. No, it's all right. I made myself look bad, and I'm crying right now, and my heart is broken, but it's okay. I'm going to try to move on. Note to self, cut that part out of the video as well. All right. So let's talk a little about entropy changes to the surroundings. So energy and temperature, right, does have an effect on sort of the entropy change that we would see in the surroundings. So for example, here on the left-hand side, we have a exothermic process. Our system is releasing the heat and energy to the surroundings there. And the result of that is when the surroundings pick up that heat and energy, we would expect everybody in the surroundings obviously to gain that energy, which means they are going to probably be moving around a lot faster, have more energy, going to create a lot more disorder. So the result of the surroundings picking up basically that energy is we should see an increase in the amount of disorder for the surroundings, which means for the surroundings, it should become more positive in this case because it's picking up that energy. Opposite would be sort of true in an endothermic process, which is like what we see over here. As the surroundings basically releases the energy or gives away the energy to the system, it's basically going to lose energy, which means everybody in the surroundings is going to kind of slow down a little bit. They're not going to have as much energy. So that's going to create a little bit more order that's going to happen in the surroundings. And we would expect to see the delta S become more negative. Again, here we're talking about the surroundings, delta S here in both of these cases. So the delta S of the surroundings is proportional, which is what that little symbol means, to minus delta H of the system or the reaction. So if we make just a little table to sort of figure this out, if we have the delta H of the reaction, and we have our delta S of the surroundings. So if it is exothermic, our delta H would be negative, which means since the surroundings is negative of the delta H, negative of a negative makes this a positive number. Yeah. So because this guy is basically negative of the delta H value, that turns it into a positive value for the surroundings. Same thing if it's endothermic. If we have a positive value for delta H because it's endothermic, negative of our positive ends up with a negative number, right? When you multiply those together, I think you still get a negative. And that is what we see here. So you see sort of the opposite effect on the surroundings, whether it's an endothermic or exothermic reaction, because either it's gaining that energy or releasing that energy. Any questions on that there? Does the actual temperature of the surroundings make a difference in how much of a change in entropy you would see for the surroundings? So let's say, for example, the temperature of the surroundings was really high. Would the additional energy coming from the exothermic reaction make a big difference? Not really, it wouldn't, because it's already starting pretty crazy with all the energy that's there. So like, if you had your oven on the 550, right, and you lit a match just outside the oven, you could feel the heat. If you take that match and put that into the oven, don't do any of this, but if you put it into that oven where it's already pretty hot, the energy, the heat coming off of the match, it's not going to make a very big difference in overall heat of what's inside the oven and stuff like that. Again, don't play with ovens and matches. Safety note, do not take out a video. All right. So when we talk about the change in the entropy of the surroundings, there's actually equation that we use, which looks really funky on the bottom there. So let me rewrite it here. So the delta S of the surroundings is equal to negative our delta H of our reaction or our system divided by our temperature, which is chemistry, which means it should be in Kelvin. Yeah, so this temperature here does need to be in Kelvin. Once again, a 273 addition to your Celsius will get you to Kelvin, which is a good conversion there. So to calculate the delta S of the surroundings, we take minus delta H of the reaction divided by our temperature there in Kelvin. To take the delta S of the reaction, we go products minus reactants from the table. We now can add both of those values together if we had them and use that to calculate our delta S of this universe to figure out whether or not, obviously, this reaction would be spontaneous or not. This equation is a really important one for a couple of reasons. First off, it allows you to calculate delta S of the surroundings. But secondly, we will see an equation that will end up looking exactly like this later on, but it will not have the negative. So negative here when you're calculating delta S of the surroundings. Later on, when we rearrange the equation, no negative. But it's oftentimes confused by people because it basically ends up the exact same thing. It's just delta H over T. So definitely we got to have that negative in there. And once again, the negative is there for that sort of opposite relationship we just talked about. As it releases energy, it becomes more positive, the delta S. All right, so why don't we try one here? So there's all the values you need. So for this one, let's calculate the delta S of the system, the delta S of the surroundings. And we want to know, will the reaction here of ammonia, synthesis of ammonia, will it be spontaneous? So I think everything you need should be up there. So take a couple minutes and see what you come up with. Here we would have to calculate the delta S of the universe to help us make that determination, which means we need the delta S basically of our reaction plus the delta S of our surroundings. So as we just talked about, our reaction is going to be our delta S of our products minus the delta S of our reactants, and our surrounding is going to be our minus delta H over T, basically. So we can start with either one, and we'll start with the delta S of the reaction here. So once again, if not provided, you would go to the table in the back of the book there to find those values. So our delta S of our reaction would be our products, which in this case is NH3. And there's two of them, which would be 2 times 193. We then would subtract it from our reactants, which is N2, which is 192, plus our other reactant there, which is H2. So that's 3 times 131. And that's going to give us here looks like minus 199 joules, right? So again, this value here does not tell us if the reaction is spontaneous or not. It just tells us what is happening in the reaction in terms of order or disorder. And does that value agree with what we see in the reaction? It should. I'm going to try this one more time to redeem myself. This is now 4 gas molecules, I hope. And this is now 2 gas molecules. So we are going from 4 gas molecules to 2 gas molecules. So more disorder to more order, right? So less things flying around, more order, less disorder. We would expect this value here, just like we got, to end up as a negative number. Any questions on that part of it there? Yeah. Of the surroundings, yeah. No, so that one's actually plus, yeah. Minus is always kind of like when you do final minus initial. So those guys, yeah. Other questions on that? Okay, so now that we have the system, let's do the surroundings. So our delta S of the surroundings would be our minus delta H divided by T. So once again, here we do need to convert our temperature into Kelvin. So that's a 25 and a 273, going to give us a 298 Kelvin. Now, here we're going to go minus our delta H, which was given to us here. Negative 92.6 times 1,000. The reason I am doing this is to get it into joules, because this guy's in joules and I'm going to have to add them together. So eventually that's why I'm doing it. You don't necessarily have to do that at this point, but that is basically why I did that there. And if you do that, we end up with 92.6 times 1,000 divided by our 298 gives us about 311 kilojoules, not like 311 there we go, joules is what I'm looking for there. Any questions on that there? Now remember as well, delta S is usually given in joules at the end, but if you did calculate in kilojoules, obviously you would be 0.311, which is fine as long as you remember when we're going to do right now that when you add these together, they need to be in the same units, right? Otherwise, you'll have the wrong answer. So since mine are in the same units, I could take my delta S of my universe here will be minus 199 joules plus 311 joules. And that's going to give me looks like positive 112 maybe or something like that there, joules. In this case, the delta S of the universe is positive. Does that mean this reaction is spontaneous or non-spontaneous? This reaction is spontaneous. So remember that a positive value for S, basically universe will mean spontaneous. Negative value would be non-spontaneous. So in this reaction, we would expect this reaction to occur. We would expect reactants to go to products. And this is also a fine example of, if you might remember, we saw this reaction when we talked about catalysts. This reaction is spontaneous, but it's super slow unless you add a catalyst to this to speed it up. But it will occur, and it will occur naturally. And that's basically all spontaneous sort of means in this context is under these conditions, if you leave it long enough, the reaction should take place. Any questions on that there? So obviously you need to be able to calculate universe, system, and surroundings for delta S, and I obviously understand what those guys mean. Okay. So a couple of things here on S. The third law of thermodynamics is a perfect crystal substance has a delta S there of 0. This is kind of like a heating cooling curve, right? And these are transitions. We have our solid going to liquid, going to gas. And obviously, as we talked about, as you go from solid to liquid, our delta S is increasing, becoming more positive, right? More positive as we kind of go that way. And obviously coming the opposite way, it would become more negative as we're creating a lot more order. If we relate this, as we will, to like the heating cooling curve that you might be familiar with when you talked about delta H and maybe specific heat and all those type of things. So for example, here, what this say is water, right? Water freezes and melts, right, at 0 degrees Celsius, right? And there's a certain amount of energy required to do just that transition, right? That is known as the delta H of delta H of fusion. Yes, good answer. That is the delta H of fusion, and that is the energy required to change the substance, right, from solid to liquid or liquid back to solid, and not change the temperature. Just solely, that's all it does is basically change the state of a substance. Because, for example, with water at 0 degrees Celsius, you have both states in equilibrium with each other. That's why it's plateaued there. You have solid and liquid happening at the same time. It's not until you get above, say, 0 degrees for liquid water to occur, and not until you get below 0 degrees that you really do get ice. But exactly at 0 degrees, where that phase transition occurs, you basically have both phases in equilibrium with each other. Same thing here, right? At this transition, at say 100 degrees for water, that is where things go from liquid to gas and back and forth. And that's the delta H of vaporization is what we use there. Again, that's the amount of energy needed to, again, just simply take the substance, like water, for example, at 100 degrees Celsius liquid water to 100 degrees Celsius gas, not change the temperature or anything like that. Delta H of fusion for water, it's about 333 joules per gram. And delta H of vaporization for water is about 2260 joules per gram, give or take a joule here or there. And these are obviously for water specifically. And as you can see from those numbers, it takes more energy to do what transition? Yeah, to go from liquid to gas, right? Because you're going from liquid where they're still kind of together to gas where everybody's broken apart. So it takes a lot more energy to do that, as opposed to as you go from solid to liquid where they're still sort of together in both sort of phases. They haven't completely broken apart. So entropy works the same way. We have as well for this transition, the delta S of fusion, which is the entropy change that occurs as you do that phase transition. And over here as well, we have the delta S of vaporization, which is, again, the entropy change that occurs at that transition. The number, right, to do the transition back and forth is the same. The only difference is the sign is different, whether it's an exothermic process or an endothermic process. We're taking a stroll down memory lane here. If I want to calculate the energy where these places here, what do I use to do that? So along, say from here, this is liquid, right? All the way liquid, all the way up there. That's all liquid. And the temperature changes, but the phase stays the same. So whenever the temperature changes and the phase stays the same, that's when you use your good friend's specific heat. Like a Q is equal to ms delta T. Good talk. All right. So, we'll think a little bit more about that in just a bit here, but we will see delta H of fusion and delta H of vaporization as well. So let's talk a little bit about Gibbs free energy here. Gibbs free energy is delta G and another letter here. And much like it sounds like, Gibbs free energy is the energy required to do some type of work, or energy that is free to do some type of work. So as we just saw and just talked about, the spontaneous process of the delta S of a universe, if it's positive number, we'll tell it's spontaneous. If it's equal to 0, it will be equilibrium. So under constant temperature processes here, we can calculate the delta G. We're actually going to see a number of different ways to calculate the delta G. This is one way where the delta G is equal to the delta H minus T delta S. So these are our normal sort of guys here. This is our delta G, which is our free energy. This is our delta H, which is our enthalpy. This is T, which is our temperature. And this is our S, which is our entropy. So there's actually a few different ways to calculate delta G. And the best piece of advice is you should just choose the equation that fits the information that's given to you. So if you were given delta H and delta S, this would be a good way to calculate delta G in that situation. If you're not given delta H or delta S, this is probably not the best equation to choose. We'll see a few in a second here that might be a better one to choose. This is also, though, the equation where you definitely want to watch out on units. So right here is our delta H, which is again in kilojoules. That's our delta S, which is in joules. And if you ignore that, you are going to be off by a factor of 1,000. So you got to really choose which way you want to convert it. You can convert it to joules or kilojoules. It doesn't truly matter. I will say that typically speaking, delta G is given in kilojoules when it's all said and done, is typically the units that are associated with it. One of the nice things about delta G is You can use the delta G of the reaction to determine whether or not a reaction is spontaneous. So you don't necessarily have to work through the whole delta S of the universe sort of situation. If you calculate the delta G and it is less than 0, which I believe means it is negative here, the reaction is spontaneous, and we would expect it to proceed in the forward direction, which means it should go from reactants to products as it is written. If you calculate the delta G and it's a positive number, that means basically the opposite is true. It is a non-spontaneous reaction the way it's written. But if you happen to reverse the reaction, that means your reactants become your products become your reactants. That means that it will then become spontaneous. So if your delta G is positive, the way the reaction is written, it's non-spontaneous. But if you reverse it, it will become spontaneous. So delta G does work very similar to sort of how delta H works. If you reverse the delta H reaction, right, the delta H sign changes. So the same thing here with delta G as well. If you did the opposite or the reverse reaction, then it will obviously become spontaneous at that point. If delta G is equal to 0, then the reaction is at equilibrium. Another way that you could calculate delta G is to calculate it based off of the standard free energy of formation, or the delta G of formation is what that stands for. Those are basically table values. So once again, you would go to a table and you could look up all the delta G values for your products, and you would subtract them from all the delta G values from your reactants. So in this situation, if you're just given the equation and nothing else and just ask, hey, what is the delta G? That's definitely go to the table and do it and look up those values. Now, delta G is very similar to delta H in the sense of what you'll find in those tables. So unlike entropy, you will once again find zeros for things like O2, N2, and stuff like that when you look it up there. When we see these sort of little knots on top of these things, you know, whatever it may be, these little guys here. What those usually mean is that has been calculated under sort of standard conditions. And when we talk about standard conditions basically means kind of like table conditions. It means pretty much what we see in here. The pressure is 1 atmosphere in those conditions. The temperature is typically 25 degrees Celsius. If it's some type of molarity, the concentration is 1 molar. So kind of when you see those little knots, it's almost standard conditions. It's almost like you calculated based off of table conditions. And if you don't see it, then something's not under standard conditions. Maybe the molarity is not under standard conditions. Maybe pressure is not, or temperature or something of that nature. So this is, again, a second way that you can calculate the delta G of the reaction, just like we did with delta S and like you do with delta H as well. Products minus reactants, kind of final minus initial state. So why don't we try one here? What is the delta G basically for the following reaction? And we got some values there on the bottom, I think. Okay, so let's take a look. So once again, obviously in the back of your book or most books, there's big thermodynamic table that has delta H, delta G, delta S sort of values on them. And that's where you would obviously go find this. Since pretty much we're just given the reaction here. So we're going to do our delta G here is going to be our delta G of our products minus our delta G of our reactants. So taking into account here, we got 12 CO2s. Each one is minus 394.4 kilojoules. We also have 6 waters here. So 6 times minus 237.2. That takes care of all of our products. So on the reactant side here, we have 2 times our C6H6, benzene, 124.5. And we're going to then add it to 15 times 0, basically. So again, if you did look it up there, it would be a value of 0. We would end up with here 12 times minus 394.4 plus 237.2. That's 2 times 124.5. Looks like if I got it right here, minus 3559 kilojoules, I think, if I punched it in right, hopefully. That means this reaction is spontaneous, non-spontaneous. The reaction will be spontaneous because we have a negative value here. So because the delta G is negative, this reaction is spontaneous. We would expect it to proceed in that direction. Any questions on that? Okay, so in this chapter, probably more than any other chapter, you may be asked questions like they really don't give you numbers or anything like that, but they go, hey, this guy's positive, this guy's negative. Would you expect this reaction to be spontaneous or non-spontaneous? So for example, if we look at our delta G sort of value, our formula here, we could use some information to help us make that decision. For example, here, our delta H, as a reminder, in terms of units, is kilojoules. This guy is joules. So this guy's got like a 1,000-fold jump already on the other side. So in this situation, if our delta H, was positive, and our delta S here was positive, in this situation, that would be positive. This would be positive. The only way delta G could end up being negative and spontaneous is you would need a really high temperature. With that really high temperature, that would be enough for this part of the formula to become a higher number than the first part and result in a negative number. So that is what it says here. Positive values on both of those. You need a really high temperature value to basically turn it into a spontaneous reaction. Obviously, at low temperatures, it's going to be non-spontaneous because you won't have enough to kind of overtake the first number there. If our delta H is positive and our delta S here is negative, so in this case, delta H minus T delta S. So our delta S here is positive. So this guy is positive. This guy is negative. And our delta H is positive. This negative will turn this negative into a positive. So no matter what temperature you throw at it, you're always going to end up with a positive value, right? So you're going to be a positive value for delta G at any temperature, which means the reaction will be non-spontaneous at any temperature you throw it at because of that negative delta S. Any questions on that one there? Now, if delta H is negative and delta S is positive, again, looking at our equation here, our H minus T delta S. In this case, our delta H is going to be negative and our S will be positive, which means no matter what temperature you roll with here, you're always going to hit a negative delta G, right? So in that sort of arrangement, delta H and delta S, negative and positive, at any temperature, the reaction will always be spontaneous, basically. So that's like your good sort of combination there. If you're looking for a spontaneous reaction, you pretty much can make it spontaneous at any temperature would occur there. The last combination would be if our delta H is negative and our delta S is negative. So once again, here looking at our equation, T delta S. So this guy's negative, this guy's negative. So this negative and this guy will then turn this side into a positive. And what that means is in order for that positive not to overtake the negative, we would need a low temperature. So the reaction would be spontaneous at a low temperature. If you get into a really high temperature in that situation, then the reaction will turn probably into a non-spontaneous reaction. So this is the way sometimes you can just look at sort of formulas and things are positive or negative. You can make that determination. And those type of questions, which are very common in a thermodynamics chapter, is you don't really give you numbers, but just kind of positive negatives. You also could just throw in values and make up values and put them into the formulas and sort of see what you end up with as well. Any questions on that there? All right, so let's try one here at 25 degrees. Let's calculate the delta G. And is it spontaneous? All right, so take a moment there and calculate it, see what you come up with. All right, so let's take a look. So as we talked about, you want to kind of choose maybe the best formula for the situation. So I have an H and I have an S given to me. So that seems like a good time to use this equation here. So putting it in here, our delta G will equal our H, which is 177.8. I'm going to multiply by 1,000. And again, the reason I did that is my S is in joules, or you got to do the other one, whichever way you want to go, to joules or kilojoules, but you need to do some type of conversion in this formula. Otherwise, you're going to be in trouble. Obviously, 25 degrees, as we did earlier, 298 Kelvin. When you add 273 to it, gives us 298 Kelvin, and our delta S, which is 160.5 joules. Putting all that together there, 177.8 times 1,000 minus 298 times 160.5, gonna give me, here we go, 129,971 joules, or since this is delta G, about 130 kilojoules, give or take. Yeah. First off, any question on the calculation? So again, you got to go joules or kilojoules. If you want to go kilojoules, is fine. Just, do 0.1778 for your, or 0.1605 for your joules. So at 25 degrees Celsius, based on this delta G value, is this reaction spontaneous? This reaction is non-spontaneous at 25 degrees Celsius, which would be like in this ballpark. And we see that because this is a graph of the pressure of CO2 in this reaction, this decomposition reaction, which means the only way that I could get pressure is I need to have produced some CO2. So because no CO2 has been produced, I got no pressure basically. So definitely at 25 degrees, we got nothing really going on. Any questions on that there? So if we wanted to determine at what temperature this reaction would become spontaneous, we could actually do that as well using the same formula. So for example, if I want to know, all right, well, I know this reaction is definitely non-spontaneous at 25 degrees, we could figure out at what temperature would it become spontaneous. And we could do that by taking delta G is equal to our delta H minus T delta S. In order for it to become spontaneous, it needs to become a negative number G, which is to the left there of 0. So we could actually, in this case, set G equal to 0. And we could solve for temperature, which means we would take T is equal to delta S equals delta H, dividing this to the other side would give us the temperatures, the delta H divided by the delta S in this case. At this point, I'm going to put the values in. Once again here, solving for my temperature, I want my delta H to be in the same units. So I am again going to multiply by 1,000 to put them into the same units, which puts them into joules. I'm going to divide it by my delta S, which is already in joules here. And when I do that there, 177.8 times 1,000 divided by 160.5 gets me approximately 1,108 Kelvin, which if I subtract 273 from gets me 835 degrees Celsius. 835 degrees Celsius is the minimum temperature at which this reaction would become spontaneous. That's pretty hot. Yes, that's pretty up there. So we'll take obviously a very large temperature. And that's what we see at the graph here. That's 835 right about there, where we actually get to 1 atmosphere of pressure, which is standard pressure. So at 835 degrees Celsius, we get actually 1 atmosphere of standard pressure. Does it start before that a little bit? It does, but it doesn't reach basically standard pressure until about 835 degrees Celsius. So this equation as well can be very helpful if you do calculate something where it says this reaction is non-spontaneous. You can actually set it to 0 and figure out at what temperature you could get it to become spontaneous at that point. Any questions on that there? This also coordinates with what we just talked about originally. Here, our delta H is positive and our delta S is positive, which means the only way for this part to overtake the front part is we need a really high temperature, which I think 835 would qualify for. Under low temperatures, as we saw in our original calculation, it would result in a non-spontaneous process occurring. Any questions on that there? All right, so let's try one here for the following reaction. Delta H is minus 1204. Delta S is minus 1216. At 25 degrees, are the reactants or products favored at equilibrium under these conditions? Okay, so once again here we have H and we do have S given to us. So I'm going to use obviously the equation that's got both of those in there. Putting my delta H in there. Once again, I'm going to multiply by 1,000 and put it into joules. And I'm also going to obviously add 273 to get my temperature there into Kelvin, which would be 298. And our delta S here, which is minus 216.4 joules. That is going to get me minus 1204 times 1,000 minus 298 times minus 216.4. Looks like minus 113.395. 12.8 joules, and we'll put it back into kilojoules. So maybe like 1140 kilojoules, give or take. Yeah. Products or reactants favored here? This is negative, which means reaction is going to be spontaneous. And if it's spontaneous, it should be heading in this direction, right? Which means products, right, should be favored here. Question on that there. This also follows what we talked about earlier. Our delta H here was negative. Our delta S was positive, negative as well here, negative. Which turns this guy into basically a positive side. So again, at low temperatures, the front guy is going to be larger. At higher temperatures, we would then become non-spontaneous, right? So this is a lower temperature, so we would expect it to be spontaneous, which is what we saw it to happen here. Any questions on that? Yeah. It would probably end up becoming non-spontaneous again, because it would allow really this back half of the formula to overtake the front number. So the front number's got a little bit of a head start to begin with, right? Because it's typically in kilojoules, which is like 1,000 times bigger than the joules part of it. So it's got that little bump. So in order to kind of get that back part higher, you need that larger temperature to bring it up over and stuff like that. So if you had something like what we saw in the previous slide there, maybe in the 900s or something, maybe, or something like that, you know, it might be enough to flip it to a non-spontaneous reaction. Yeah. Other questions? All right, we were laid up there for today.